السلام عليكم يا شباب، صباح الخير.
السلام ورحمة الله.
حياكم الله جميعا. Okay, so last class we talked about, if you remember, one of the, I think in my opinion, I'm not going to say it's the most difficult concepts, but it's, I'm not going to say it's the most, but it's clearly one of the most difficult concepts, not only in our course, but الحقيقة in many EE courses. يعني, I'll say it this way. Maybe what I'm saying right now is kind of an exaggeration, but if you can solve a problem of, relatively speaking, a complicated problem of convolution, you probably can solve any problem in electrical engineering. As I mentioned, this might be a kind of an exaggeration, but honestly, convolution is one of the things, one of the topics I think that most electrical engineers hate to be faced with. Now, I'm not saying that throughout the course in here we're going to be using convolution. In fact, you'll see later on we'll talk about, let's say, techniques that will allow us to solve or find the output of a system without doing the convolution. Yeah? But inshallah, wait, maybe in a week or 10 days or so, we'll talk, probably less, maybe in a week or so, we'll start talking about something called the Fourier transform. In fact, later today we'll talk about something called the Fourier series, and later we'll talk about something called the Fourier transform that allow us to analyze systems and basically find the output without doing the convolution. Okay, I promise you that we'll do this. But yet, you need to understand how to do the convolution. Okay, so let me continue what I was discussing last class. In fact, while preparing for the lecture last night, I was thinking, and the lecture notes there, the part that I have to the bottom, needs to be updated. I have this table, you have seen it before. Yeah? I did not update it completely, I just did a little bit of update. So this is still not valid. In fact, to discuss this topic, I will have to go to the previous table. But while I was preparing for the lecture note, I was thinking, should I solve another problem on convolution? I thought, at least let me discuss something related to convolution that is of importance, at least to explain to you some of what I'm going to mention in that table, in the second table that looks like the first table that we talked about several classes before, when we talked about the properties of continuous time systems. Okay? And the convolution example that I'm going to be talking about in here is this. I haven't put it yet, but inshallah I'll add it there. Okay? What if someone told you that I have x of t, which is equal to, for example, okay, yeah, let's say x of t, for example, is equal to an impulse h, so delta of t. Okay, and I have, you know, what do you call it? I have a system which has an impulse response h of t. Okay, and let me just give you an example of h of t. Let's say that h of t is equal to the following. It's equal to 0 when t is less than 0, and it's equal to e to the power of minus t. I'll make it a little bit simple, okay? When t is greater than 0. Assume that I have the following system. A system with an impulse response that looks like this, okay? And the input to that system happens to be an impulse, okay? So this is basically what I have. I have a system with an impulse response h of t, and let me sketch it. H of t appears to be like that, and it's, let me use a different color. Assume that this is the impulse response of the system, okay? And I'm feeding to that system an input x of t, which happens to be delta of t. Okay? And someone's asking you, what is y of t? Can anyone tell me right away what is y of t? Without doing a convolution. Can you or you cannot?
Can we again review the...
I didn't hear you, Abdul, but Saleh, can you maybe answer me?
Shouldn't be h of t?
Absolutely right, yes. Okay. What did we say the impulse response of a system? What is it? It's the output of the system when you feed an impulse. And this is exactly what I have. I'm feeding an impulse to the system, which has an impulse response, h of t. So clearly, y of t will be equal to h of t. Now, the question is, assume that you didn't know this. You didn't know that feeding an impulse to a system that has an impulse response, which is h of t, will provide you with the output that is equal to h of t. Can we prove this? Or will, let's say, the mathematics, and what I'm trying to say is, if we convolve, if we find h, or let me say, if we find the convolution of delta of t, so thank you so much, Saleh, for answering me. You're absolutely right. Is the convolution of h of t with h, I'm sorry, delta of t, I'm sorry, I don't know why I keep saying, okay, is the convolution of delta of t with any function h of t, is it equal to h of t? This is basically what I'm trying to hint to. If I convolve any function with delta of t, will the output of the convolution be equal to the same function, h of t, or not? It should. According to this, it should. And in fact, it will be. But why? Let's see. Let's apply the convolution. What does the convolution say? The convolution of any two functions, x of t and y of t, or whatever, two functions, okay, is always equal to the integration from minus infinity to infinity. In fact, its solution or its answer is quite simple. Yeah, we're not going to have to do that complicated process that we did before. So the convolution is the integration from minus infinity to infinity of delta of tau multiplied by h of t minus tau, d tau. Or we can write it, in fact, let me write both forms. This one form or the other form is h of tau multiplied by delta of t minus tau, d tau. Let's see, do we get the same answer for both of those or not? Remember, when we said when you multiply any function by an impulse, what does the impulse do? Remember the properties of the impulse function when we discussed them, the 4 or 5 properties? Anybody can remind me? Fadal Abdurrahman.
Symmetry.
No, this is not symmetry here. You remember, we mentioned that delta of t minus tau, for example, is equal to delta of tau minus t. This is the symmetry. Okay? But there was another property. Do you know it, Abdurrahman, or should I ask maybe one of your friends?
No, I don't remember, to be honest.
Okay, طيب, no problem. تفضل محمد.
U of t minus tau.
What do you mean by u of t? You mean
I think the answer is u of t minus tau.
The output, you mean here? Here?
Down.
In here? What? Where did you get the u of t?
Yes.
How did you get the u of t?
Because of delta.
Okay, يعني I think you're on the right track, but the u of t, I'm not sure exactly how you got it, Muhammad. Yeah, this is, I was maybe, okay, let me go to the properties and maybe you can tell me which one will help us. If you remember the properties that we had somewhere in here. When we talked about, okay, this is the impulse. Okay, this is the impulse. If you remember those 4 or 5 properties. In fact, it happens to be the first one. You remember this? What do we say? Whenever you have any function or any signal, x of t, that multiplies an impulse, what does that impulse do to you? It basically it removes all of the values of the signal, x of t, and only says, I want you, your function, x of t, to cancel all of your values. I'm only interested in one of your values. Which of your values am I interested in? It's the value that exists where I am. So think of me as the impulse function, and someone is multiplying me. Some other function is multiplying me. I'll tell that other function, I don't care about all of your other values. I exist, for example, at t equal to t0. At a specific time, into a function x. Sorry, I'm speaking on behalf of functions, okay? I hope that you're not laughing. But basically, I, as an impulse function, I'm telling the other function, I don't care about all of your other values. All I care about is your value where I exist. Where do I exist? I exist at the point t equal to t0. And if I sketch, this is the delta, it happens at t0. This is basically what delta of t minus t0, this is how it looks like. That function says, I don't care about all of the values of x of t. I don't care about this. Let me just label them in blue. I don't care about this. I don't care about this. I don't care about this, or this, or this, or all of those values are not important to me. The only value that is important to me is the value of the function x at that point, because it is the value that will multiply the impulse. All other values will be multiplied by 0 in here. The impulse is 0 here and 0 there. And this is basically the property that I was hoping you would tell me. It will help us. In fact, we are using this in the second property here to tell you that now once you do this, once delta of t minus tau, delta t minus t0 in this situation, okay? I'm not using tau in here, but I'm using t0. Once this impulse feeds its location into x of t, okay? So we have x of t0. This thing now becomes a constant. It's not a function of time. And the integration is a function of time. Or let's say the integration is with respect to time. So I can take this thing outside. And what remains for me inside is the integration of the impulse. And we said there was another property which happens to be, in fact, this is the definition. It's not really a property, but it's the definition of the impulse itself. The integration of any impulse, as long as the impulse is inside integration, then you always get 1. So what remains for us in here is the integration of the impulse, which turns out to be equal to 1. So we end up with x of t0. Now let's apply the same thing that we have in here. Let's apply it down. Still need to go further. We're close. The computer is a little bit slow because, by the way, I've added a lot of material. If you look at the lecture note now down, the lecture note that I uploaded to you, I think was 43, 45 pages or so. Now it's 75. It doesn't mean that last night I added, or let's say I typed 30 pages or 25 pages or so. It's just that the material that comes next, I already wrote part of it for another course. So I copied it. In fact, EE207 a long time ago contained the material that we're going to be talking about in the next 2 weeks or so. Right? So I just borrowed it from there. Clearly, I'm not going to write it again. I just need to fix it and adjust the figures and so on. Because when I wrote this material, this was maybe 15 years ago. So the material was, it was even not written in the same format that I'm writing the lecture notes now. So I have to fix it. But anyway, most of the material is there. Right? So now let's look at this. How does this look like? Isn't it exactly the same concept as what we have above? I have a function h of t minus tau or whatever. It's a function. And it happens that this function multiplies an impulse. It's just that the impulse is written here before the function h. While up, I had x written before the impulse. In here, the impulse comes first. Above, I had the x coming first, not the impulse. But the concept clearly is the same because they are two functions that are multiplied by each other. Okay? So now I have h, which multiplies a function, which multiplies an impulse, and it happens that this impulse happens at t equal to 0. Now this happens at t equal to 0. So what should you do? You should take that t equal to 0 and substitute it for tau. Remember that the x-axis now is not t, the x-axis is tau. So if you wanted to plot, this is basically what I have. I have an impulse, this is tau, and I have an impulse that happens at 0. And I'm multiplying this impulse by a function which I'm calling h of t minus tau. So what will this impulse do? It will take its location, which is tau equal to 0, and say, I don't care about all of the values of this function. I'm only interested in the value of the function h, where I substitute, I remove tau and replace it with 0, because the impulse happens at 0. So I will remove the tau and replace it with 0. Okay, so I'll end up, this part basically, let me write it this here. So this first thing is going to be equal to the following. This is equal to the integration from minus infinity to infinity of delta of tau as it is, multiplied by h of t minus 0, or basically h of t d tau. Now you may say, well, this looks different from the one that I have above. No, it's not. It's actually not different, except that above I had t0 being a constant, and t was the variable of integration. In here I have tau being the variable of integration, and t appears to be just a constant. It's a value, 3, 5, whatever. With respect to the integration itself. With respect to the integration, I'm not integrating with respect to t. I'm integrating with respect to tau. So all of this is a constant with respect to the integration, so I can take it out. And what remains for me inside the integration is just the delta, which will become equal to 1. So this becomes equal to h of t. Let's look at the second one. Does it give me the same? Yes, except now that the delta here happens at t equal to tau. So I will remove every tau in here and replace it with t. This is closer to the one example that I have above. This is closer to the one that I have above, because over there I didn't have the x shifted. It was just x of t. And now in here I have h of tau. And in there I had the delta shifted by t0. In here I have the delta shifted by t. It's shifted and flipped. Okay. So I will have to evaluate this function at the location that the impulse happens. And this impulse happens at tau equal to t. Or tau equal to t, maybe I should have written it this way. Okay? So take the tau and remove the tau from the function h and replace it with t. So again, this becomes a constant. I can take it out. And what remains in the integration, this is the integration from minus infinity to infinity. What remains inside the integration is just the impulse, which will turn out to be equal to h of t. Okay? So, yeah, what I'm trying to say, gentlemen, is that if you convolve any signal, the purpose of this example is that if you convolve any signal with an impulse, the output is exactly the same signal. Okay? If you convolve any signal with an impulse, the output is exactly the same signal. No change in it. So convolving with an impulse does not change the signal. Except that there's just one small thing that I did not discuss. What if instead of putting x of t being a delta, what if I put delta of t minus delta of t minus t0? What will happen in this situation? Exactly same example. I'm putting this into this filter or into the system that has an impulse response. By the way, I did not solve it for that impulse response. Okay, but if I plugged in instead of h of t, I plugged in e to the power of minus t. Okay, you'll see that the output will be exactly the same. Trust me, it will be exactly the same. Okay. Now I'm putting an impulse into a filter or into a system, okay, in which that impulse itself is shifted by t0. What can anyone guess? What do you think the output will be? Will it be equal to h of t? Or will it be something different? Any guesses? What guesses? Fadal Abdurrahman.
Just can you repeat the questions? I couldn't understand.
Okay, sure, no problem. Okay, what I said above is if I have a system with an impulse response h of t, and you feed delta of t, the output becomes h of t. So this is what we said above, and I have proved it to you. Okay, what if I have the same system h of t, but I don't feed delta of t, I feed delta of t minus t0. Yeah, the shifted version of that delta. What will the output be? Okay, Fadal Muhammad. Muhammad Al-Jani.
The output will be h of t minus t naught.
Absolutely right. Yes, perfect. Okay. Probably if the others also had the same answer, you would be correct. Okay. So in fact, because I didn't, you see, this comes from different, or there are different ways of proving it. You remember when we said we are setting, or we are talking about the impulse response there for specific type of signal, or I'm sorry, specific type of systems, and those systems are linear time invariant systems. What was the meaning of the system being linear? We understood what linear is. If you add two signals, two inputs, the output becomes the addition of the two outputs, two previous outputs. This is what linear means, but this is not our concern. And here we're not testing the linearity of the system, or we're not using the fact that the system is linear. We are using the fact that the system is time invariant. And we said that for time invariant systems, if you delay the input by a specific amount, the output gets delayed by the same amount. This is one way of just proving it. And if I gave you something like this and told you, prove that this is going to be h of t minus t0. There are two ways of doing it. One way of you can say, look, you have said that this is true. The upper one is true. And this is a linear time invariant system. The fact that it is time invariant means that if I feed an input which is delayed version, all you have to do not do the solution from scratch. Look at the output that you got before and just delay it by t0. And you get basically that. And this is absolutely right. Okay? So what Muhammad mentioned is absolutely right. Perfect. There is another way of doing it, which is basically doing the math. Let's do the math exactly in the same concept. And let me just erase this. I'll just do one form. And there's no benefit in doing two forms because trust me, you'll get exactly the same answer for both. So let me now feed delta of t minus t0. So now the output y of t will be equal to the integration from minus infinity to infinity of, remember, this is how you do the convolution. Let me take h of tau, okay, multiplied by the first function where you remove every t and replace it with t minus tau. Remember, when we had, let's say, x of t, sometimes, by the way, I keep repeating things, but I just want to make sure that you understand them. And h of t, how did the integration, the convolutional integral, how did it look like? I took this thing and plugged it there, but removed the t and replaced it with tau. I took this thing and put h of t minus tau, right? And the integration is with respect to tau. Let me do exactly the same thing in here. Y of t is equal to the integration from minus infinity to infinity of, let me take any one of them. I can start with any one of them. It doesn't make any difference. Let me take this to be the first. So instead of h of t, I'll put h of tau. And instead of this, I'll put it there, but I'll remove every t and replace it with t minus tau. So it will be delta of t minus tau minus t0. T0 is from the input. Yeah, it's a shifted version, or it's a delayed version of an impulse. D tau. This is basically the convolution that I'm planning to do. Now remember that the convolution or the x-axis is tau. I'm integrating with respect to tau. So find where is the location of this. If I plot, and this is, by the way, this thing sometimes confuses a lot of people. If I have the x-axis there being tau, where's the location of this impulse? Is it at t, tau equal to t? Is it at tau equal to t0? Or is it somewhere else? What do you think? Any guess? Wild guess. It's okay. Make a mistake. No problem.
Sorry, Doctor, can you repeat that question?
I'll repeat the question. Okay. We said that if you have, no problem. Repeating the question means probably I didn't say it well. Okay. If I have the x-axis t, and I ask you, where is delta, or sketch delta of t minus 3? Where does this function exist, or where does the impulse happen?
At t equals 3.
At
3 units to the right.
Yes, exactly, at t equal to 3. So both of you mentioned it right. Okay. So this is equal to 3. Okay. So the impulse will happen there. طيب, what if I change this t to tau and change this t to tau? What's the location of this impulse? Exactly the same location. T is just, think of it as a dummy variable. It's just, I could put it alpha, I could put it t, I could put it what? As long as this is the same as this, the location of the impulse will be the same. طيب, what if I told you I have this the x-axis is tau, and I have an impulse which is delta of t minus tau minus t0. Is this impulse, I'll do it maybe in two different ways. Is this impulse, or I'll give you different solutions or answers, and let me know which one you think is the most appropriate. Is it going to be at t0, or is it going to be, depending on t0 and t and so on, one of them could be to the left, one of them could be to the right. I'm not interested in the specific values of those. Or is it going to be at t, okay? Or is it going to be at t minus t0? Let me just fix it. Yeah, if the answer, if I gave you the following answers, A, B, C, D, E, maybe F, which one do you think is the correct answer? The location, this is the location of the impulse. Is it at t? Okay, if you have an answer, keep it, just give me a minute. Is it at t? Is it at t0? Is it at tau? Is it at t0 minus t? Okay. Is it at t minus t0? Is it at t plus t0? Or maybe A, B, C, D, E, F, G? Is it at minus t minus t0? Okay, let's see. I'll pick by random. Hamad Shahri.
T0 minus t.
How did you get this? At t0 minus t. How do you get it? Maybe. I'm not, honestly, I did not think about it, but probably what you're saying is right. How did you get it?
I took minus common factor.
Okay.
So we have tau.
Okay.
Minus t plus t0.
Plus t0. Okay. طيب. But how does this help?
So the shift will be t0 minus tau.
Okay.
Or t.
What you said is right. Okay. I thought of it in a completely different way. You see, when is the impulse? When is delta? What should you put in there so that the delta happens? And the delta occurs. What is the value that if you put there, you suddenly see a delta? 0, isn't it? Isn't delta of 0 equal to infinity? And delta of any other value other than 0 is equal to 0, صح?
Yes.
Okay, so set this to be equal to 0. Set the thing that is inside there to be equal to 0. So t minus tau minus, this tau, minus tau minus t0, set it to be equal to 0. Now the x-axis is tau. It's not t0, it's not t. So take tau to one side, and this will tell you where is the location of the impulse. Okay, so take tau to the other side, let's say, so that we write it as tau equal to, okay, and we'll end up with the following. Remove this. So it's t minus t0. I think this is the answer that you gave me, right? So it's in fact this part. Okay, so in fact, this impulse happens at t minus t0. It doesn't happen at t0. It doesn't happen at t. Remember that t0 is just a shift. T with respect to this integration is also a shift. Okay, it's just a constant. Yeah, think of it as a constant. So take those two values and replace them, or the difference between those two, and plug them in place of tau. And now this. Sorry, I know that I made a mess in here. Okay, but I hope that you were following me. Okay? So once I take t minus t0, let me just fix a little bit. Sometimes when I see the mess that I make, especially when I'm using this computer, I think that this cannot be fixed. I have to delete everything and start fresh. T minus t0. Okay, but I'll try. So basically, this now needs to go and replace tau. Now, h of t minus t0 is just a constant. It's not a function of the variable of integration. So I can take it out, and the remaining thing, which is the integration of the impulse, becomes equal to 1. So I'll end up with h of t minus tau. And this is basically what, don't remember who, I think Muhammad answered. Okay, so basically this is true. This is, yeah, we kind of proved it in two different ways. Okay, right. There is a reason why I'm talking about the impulse, the convolution with the impulse. Okay, and it has to do with the properties of systems. Now you're going to say, you gave us a table above in here, which is similar to that table. My apologies, I did not have time last night to finish it. I became busy. I was grading the quiz of the other course. Right? I haven't graded your quiz yet. Quiz number 2, I mean. If you remember this was the table that you had in the lecture notes. We're talking about 6 or 7 properties for systems. Now, why am I repeating the table there? I'm not actually repeating the table, and it's the same concept, except that when we discussed properties of systems in this table, if you notice, I always gave you the output of the system, or the examples were always the output y in terms of x. And this type of relationships, we called it the input-output relationship. Tell me what the input is, I'll take the input, plug it in that relationship, and I'll tell you what the output is. The same thing here, the same thing there, the same thing, all of them, in fact. Y, eventually, I'm relating y to x, okay? I'm relating y to x, and so on. Okay? In all of the properties of the system, I was relating y to x. And based on this, I was telling you whether that system is stable or causal or time invariant, and so on. Now we started talking about linear time invariant systems. And we said that in linear time invariant systems, I do not need to give you y equal to some transformation of x of t. This is typically not what we do with linear time invariant systems. I could still give you this. But typically, if I'm talking about a linear time invariant system, the way I describe the system is not this form. This is not the way I usually use. I can use it, but it's not typically what you'll be using. So how do we describe systems that are linear time invariant? We said you describe them with their impulse response. So now let's talk about the properties of linear time invariant systems. So I will go over all of those properties, more or less, and discuss how does the impulse response appear for a system that is, for a linear time invariant system that has memory, and how does it appear for a linear time invariant system that does not have memory. How does the impulse response look like for a system that is invertible, and how does the impulse the impulse response for a linear time invariant system that is not invertible look like, and so on. This is basically what I'm trying to do. Unfortunately, I did not have the time to complete the table below. So let me work on this table. Okay? Now, there are 2 of the properties that I'm not even going to touch. What are those? We said that we are limiting ourselves to, the reason why we're using the impulse response is that the system is linear time invariant. So can you have a linear time invariant system with an impulse response that is h of t that is not linear? You understood what I just said?
No.
Can you have a linear time invariant system with an impulse response h of t? Yeah, because the system was linear time invariant, I was able to get h of t. So can you have a system that has an h of t that is not linear? No. Clearly, because we are saying that it is linear time invariant. So I shouldn't even discuss this property, whether it's a linear or not. It has to be linear, because if it was not linear, I wouldn't be able to get h of t. And the same thing with the time invariance. If it was not time invariant, if it was time varying, okay, I wouldn't be able to get the impulse response in the first place. So clearly, if I have a linear time invariant system with an impulse response h of t, it has to be time invariant. So those 2 properties, I will not discuss them. I will probably focus on the upper ones. Okay? Right. Now let's look at a memoryless system. What do you think the impulse response h of t of a system that does not have any memory? How does it look like? You see, for a system that had no memory, where you're describing it using the input-output relationship, the input and output were all, or the output only depended on the current input. It did not depend on the previous input or on future inputs. While a system that had some memory, the output depended on either previous inputs or future, previous inputs or future inputs. Like, for example, the example that I have in there. What do you think this translates to when I'm talking about the impulse response? How does the impulse response of a system that is memoryless, let's start with a system that is memoryless, that does not have any memory. Remember what I talked about when I just talked about the convolution of h of t with an impulse. Maybe this will give you a hint. Any ideas? If you don't understand it, or if you don't know, don't worry. Maybe it's kind of it's an advanced topic, or I know it because I have worked with those systems a lot, but probably it's new to you. Okay. The reason why I talked about this, gentlemen, is to tell you about the convolution of any signal with an impulse gives you basically that thing. Is to tell you the following, that for an output y of t to only depend on x of t is equal, for example, to x of t, or 3x of t, or so, the impulse response of the system should be only an impulse that exists at 0. What do I mean by this? If h of t is equal to delta of t, if this is the impulse response itself, if the impulse response of the system itself is an impulse that exists at 0, okay, then y of t, or the output, we know that the output is nothing but h of t convolved with x of t. Think of it this way. If I have any system, okay, and any system, and the output y of t is any linear time invariant system, and the output is certainly, in all situations, the output is always equal to the convolution of h of t with x of t. Let me write it as x of t convolved with h of t. It doesn't make any difference, but x of t convolved with h of t. This is a property of all linear time invariant systems, and we proved it last class, in that, or 2 classes ago. Right? Now, if I want y of t to be equal to x of t, or some constant multiplied by x of t, but let's, just for the sake of argument, let's say that I want a system in which the output is all equal to the input. If this is the situation, then we say that the system is it does not have any memory. What should h of t be, so that if I convolve it with x of t, the output becomes x of t? Any thoughts? Yes, if you have any thought, just say it. It's okay. Okay. If you don't have any thoughts, okay. Let me just maybe emphasize, or let me just stress this point so that you understand it, gentlemen. What we said before, and I hope that I can explain it well. For any system, this is true. For any linear time invariant system, we're discussing now linear time invariant systems. The green box there is always true. And for a system that does not have any memory, that is memoryless, the output should only depend on the input at the current time. I should not have, for example, something like this, x of t minus 1, or x of t plus 1. This should not happen for a system that does not have any memory. For a system that does not have memory, I should not have any component that looks like this. So one possible example is that y of t is equal to x of t. Meaning, put the input, you see it at the output, without any change. This is basically what it means. This is like a box where I put an input x of t, and I always find the output is x of t. This is a memoryless system. You're putting a signal, you're getting the same signal at the output. Not delayed, not advanced, nothing. Nothing, no change happens to it. Is this a good system? Probably not. It's just like a wire that does nothing to the signal. But nevertheless, you can think of it as a system that does nothing absolutely to the input. Now, the question is, if I want to satisfy both of those, y of t is equal to x of t convolved with h of t, and y of t is equal to x of t, what should h of t be? So that if I plug h of t in here and I convolve it with x of t, I get the output equal to x of t. There is only one possible solution for this. تفضل عبد الرحمن.
I can only think of delta. Delta of t.
Absolutely. Yes, delta of t. The only thing that will give you this is if h of t is equal to delta of t. And I have shown you just a few minutes ago that if you convolve any signal with an impulse, the output is exactly the same signal. Right? Now, there are other possibilities, okay? And the other possibilities is if I put 2 delta, or if I put 5 delta, and some constant multiplied by delta, some a multiplied by delta, where a is a constant. All of those, clearly in this situation, the output is not going to be equal to x of t, but it will be equal to a multiplied by x of t. Okay? So if you have a system with an impulse response that is equal to some constant multiplied by delta of t, then the output will be equal to the input multiplied by some constant. And this is the only situation in which you will have a memoryless system, a memoryless time invariant system. Any other system, just delay this delta of t, make it delta of t minus 1, and you see that now y of t will be equal to a shifted version of x of t minus 1. This is what we said also a few minutes ago. And if y of t is equal to a x of t minus 1, this is not a memoryless system. This is a system that has memory. In fact, the output now depends on the input 1 second ago, which means that it has memory. Okay? So the only way for me to have no memory is that the impulse response of the system is just a constant multiplied by delta of t. What do we call a system that has an impulse response that is equal to a multiplied by delta of t, if this is h of t? What type of system is this? I'm sure that you have seen it. You have maybe used it. You have used this system, and if you have taken, I don't know, EE203, for example, you have seen it. Yeah, what type of system is this?
It's just an operational amplifier.
Absolutely. This is an amplifier. This is an amplifier. Thank you so much, Abdurrahman. Okay? An amplifier is something that takes a signal and amplifies it by a factor of 5 or 10, or even attenuates it. Okay? You can think of an amplifier as something that makes a signal stronger, or maybe reduces the signal. There's no benefit in reducing a signal. There are some benefits. But I'm saying that an amplifier that you get, you pay money to buy it, and then it attenuates the signals for you is kind of silly. But nevertheless, you can think of an amplifier as something that will increase the amplitude of the signal or will reduce the amplitude of the signal. Okay? An amplifier will always have an impulse response that is equal to A multiplied by delta of t. Not A only. Something that has an impulse response which is A, no, that's completely different. And maybe I'll talk about it later. But something that has an impulse response which is A delta of t, okay, is let's say an ideal amplifier, or as Abdurrahman mentioned, an operational amplifier. Operational amplifier, by the way, is just one type of amplifiers. There are thousands of amplifiers, okay? It's basically what we call an ideal amplifier that takes an input and produces exactly the same input but with higher amplitude or lower amplitude. And there is a very important feature in that system, an amplifier, that makes it memoryless, is that the output is not a delayed version of the input. The output is not delayed version of the input. If the amplifier delays the input by 1 second or 2 seconds, it is a memory, or it's a system that has memory. Okay? Typically, by the way, even if you have the best amplifier in the world, and you put a signal, you'll always find that the output is slightly delayed. Why? Because the amplifier is made out of electronics, and all electronics require a little bit of time to respond to the input. Meaning, if you put a signal, which is an impulse, you don't expect the output will be exactly an impulse at the same time. It will be slightly, maybe by 1 millisecond or 1 microsecond delayed. It depends on how complicated that amplifier is. But there will always be a small delay. But in here, we're talking about an amplifier that is an ideal amplifier, let's say, that does not delay the signal. Okay? So to maybe answer or to put in here a system that, if I wanted to put examples for this, so I'm not going to use those. H of t in here. Let me use red. Maybe it's or black. I think it's clearer. H of t in here might look like, for example, 3 delta of t minus 2. Okay? That system has memory. While in here, h of t is equal to 5 delta of t. or some constant multiplied by delta t. This is a system that does not have any memory. Okay. So let's go to invertibility. When will a system be invertible? Let me again do something similar to what I have done in here. Let me erase the mess that I have there, and my apologies for that big mess. Sorry. What just happened? I wish that whiteboard, by the way, you could just look at, let's say you have a lot of text that is written on a whiteboard, a regular board, yani, okay, green board or whiteboard, and you just make, I don't know, a curve around the text that you want to delete, and it just disappears, like those smart boards or so. Unfortunately, you have to use that eraser, and especially the boards that we have in many buildings in here are the green boards that use the chalks, and the dust is not healthy. But by the way, the university has changed a lot of boards in many buildings now. They are in fact in the process of changing some of the boards to smart boards, or I don't know, computer computer screens and so on. So when you come back to the university, you'll find that there are a lot of changes that happened during the past year. Okay, so let's now talk about invertibility, and let me say the same concept. We said that a system is invertible if you do this. When is a system invertible? If when you put an input, x of t, let me just remind you, if a system is invertible, if when you put inputs, different inputs, each input will result in a single output, okay? And not only that, each output comes from a single input. Meaning, for example, if I put two inputs into a system, and I get the same output for those two inputs. Like, for example, if the output is equal to the input squared, or the absolute value of the input, or something in which there are two inputs that I can feed into the system and get the same output, the system becomes non-invertible, right? Now, what is the feature in any system that is not invertible? It must have a feature in it. Yeah, maybe let me give you a hint. Can you have a system that is invertible with an input? Let's say if this is the input and this is the output. Okay. Is this system invertible or not?
Yes.
Something that looks, yes, it is invertible. Okay. Why? Because for every input, let's say there's one output. Okay. Now, is this system linear, by the way?
Yes.
No, this system is not linear. The way I have sketched it, I hope that maybe I didn't sketch it maybe well. Is this system linear?
Oh, okay.
I'm sorry, maybe it resembled a straight line, but I didn't mean for it to be a straight line. But now, is this system linear?
No.
The green curve. You think it's linear? No. Double the input. How do you know that it's linear? Put an input here, you get an output. Put another input, you get another output. Now, if I add those two inputs, do I get the addition of the two outputs? No, because this is, for a system to be linear, its input-output relationship has to be a straight line. Like an amplifier. If you double the input in the amplifier, the output doubles. If you reduce the input by 1/2, the output reduces by 1/2. An amplifier is a linear system. Okay. However, this system, the way that I have sketched it, this curve e to the power of x or something like this is not linear. Now, what do you notice about the two systems that I've mentioned? For example, the absolute value. How does the input-output relationship look like? This is the absolute value. And what about x squared? X to the power of 4. Maybe I'll do a different color. X to the power of 4 looks like this. What do you notice about all of those systems? Are they linear? Do you think that any of those three systems that I've sketched there are linear? تفضل فيصل.
No, they failed the horizontal test.
Exactly.
Not linear.
Even yes, you're absolutely right, Faisal. Okay. Even the absolute, clearly this is not linear. X squared is not linear. Double the input in x, and double. Let's say if I put x as an input, I get y equal to x squared. Let's say, for example, 2, 4. Okay. If you double the input, this is the simplest way probably of detecting whether it's linear or not. Although it's not. Sometimes if you just try two numbers or so, it may appear to you that the system is linear, but it's not. Okay, so you have to try multiple numbers. But one way of detecting whether a system is linear or not very easily is put an input that is equal to 2, you get the output equal to 4. Double the input, 4, the output is 16. It's not double the previous output. It's not 8. So it's not linear. The same thing with x to the power of 4. So x to the power of 2 and x to the power of 4 are not linear. Okay. What about absolute value of x? Now, absolute value of x, if y is equal to absolute value of x, is this a linear system? It may look like it's linear. Why? Put x equal to 3. You get the output y equal to 3. Double the input, x equal to 6. The output is equal to 6. It looks like it's linear. No, it's not always linear. It might be linear for specific values, but it's not always linear. Let me show you. Put the input equal to -3. Okay, the output is equal to 3. Yeah, let me say input output. Input. The output becomes equal to 3. Okay, let me put another input which is equal to 5. The output is equal to 5. Add the two inputs. 2. Is the output equal to the sum of the two? When you put 2, clearly the output will be equal to 2. Okay, is this 2 equal to the sum of those two? No, so it's not linear. Why did it become linear, or why did it appear to be linear when I took some values and not linear when I took some other values? Because the point is that the absolute value is made out of two straight lines. If you take two inputs that are on the same side of the straight line, it will appear to you like it's linear. But if you take one input on one side and one input on the other side, you'll start to see the nonlinearity of the absolute value. Yeah, if you take one input in here and one input in there, you start to see that nonlinearity. If you always take two inputs that are on the same side, it will appear to you as linear because the function, the output, is related to the input by a straight line in that region. Okay, I hope that you understand this point, right? So now the point that I'm trying to make here is for a system to be non-invertible, it must have some form of nonlinearity. If it is linear, you see that the output is always related to the input by a straight line. Not, at least, or let me say this way. For the system to be invertible, or let me maybe say it in a different way. We're talking about linear time invariant systems. And one of the features of linear systems, linear time invariant systems, is that they are linear. Which means that their input-output relationship is always a straight line. So it's always a straight line, like that. Which means that can I have a linear time invariant system that is not invertible? What do you think? Can you have this?
Of course not.
Of course not. Yes. So this is basically the concept. Okay. What I'm basically saying here is you'll never have this. A system. Sorry, this is invertible. Sorry. Okay. You'll never have a system, linear time invariant system, that is not invertible. Why? And this is in concept. It doesn't mean that every. Okay, I'll come to it when I talk about the next point. Okay, but think of it this way: the nature of linear time invariant systems is that they are linear, and linear systems you should always be able to invert them. Let me leave it at this. Okay, right. Now let's go to the next point, which is the inverse of a system. Now we said that it's invertible. Okay, so I should be able to find an inverse to a linear time invariant system. Now, this is sometimes easier said than done. Theoretically, you can always find an inverse. to a linear time invariant system. But finding that inverse is not always easy. Sometimes it's very difficult. Okay? Let me talk about the inverse of a system. Assume that I have a system, and I hope that you'll understand what I talked about when I said the convolution of any signal h of t convolved with delta of t minus tau, or minus t0, let's say, is equal to h of t minus t0. Remember this. What does this mean? If I put an input, or let me do it maybe in a different way. So sorry for that. Okay, so that you'll understand the concept. Let's say I have x of t in here, and I'm convolving it with h of t, and h of t happens to be equal to delta of t minus t0. So clearly the output will be equal to x of t minus t0. When t happens to be equal to delta of t minus t0, then the output becomes a delayed version of the input. We agreed on this before. Okay. Now let's say that I have a system in here with an impulse response that is equal to delta of t minus t0. Okay. And I'm putting x of t here. We said the output will be equal to x of t minus t0. What is effectively this system? What can I call this system? A system that takes an input and provides me with an output that is equal to the same, but at a different time. What is this system? Any ideas? It's called the delay. Well, okay, yeah, memory. If you say memory, probably that's okay. But usually we call it a delay. Okay? And there are, in fact, in different systems, there are blocks that will cause a delay. And you put into them a signal. Now they'll provide you with that signal after 1 hour, or not 1 hour usually. Yeah, you can have a system that will provide you with a delay of one year if you want. Okay, but typically in an electronic device or so, the delays there are in milliseconds, microseconds, or something like this. Okay, but nevertheless, this is a delay. Here's the question that I want to ask you. What can I put in here? What type of system can I put in there such that I get exactly the same input that I had there, which is x of t? What should the impulse response of that system so that it inverses the original one? Tfadal, Abdurrahman.
So it will be time advancement, delta of t plus t naught.
Absolutely right. Delta of t plus t naught. Okay. Now, can you have? You see, I have about 2 minutes. Like, I think I'll stop at this point. Okay. And I'll leave this figure, inshallah, in here because we will talk about. Okay. The next item is causality. We've talked about inverse. Okay. Next class, inshallah, I'll continue on this point. I'll talk about which systems have an inverse and which systems maybe they don't have an inverse, or let's say they have an inverse, but their inverse is quite difficult to find. Okay. So I'll continue next class, inshallah, from this point, and I'll talk about this thing when we talk about causality. You see, just to give you an idea, this system is a system that takes an input and provides an output after 2 seconds. What does this system do? It takes an input and provides you with an output before the input happens. And this is what we call non-causal systems. Those systems do not exist in real life. Okay? But anyway, in theory, you could have a system that would provide you with an output before the input comes. Those are called non-causal systems, while this is called a causal system. So what I'm saying in here is that my discussion about this topic or about this point kind of covers multiple points. Okay? But inshallah, next class we'll start from this same point. If you have any questions, I'll be happy to answer your questions. If you don't have any questions, inshallah, I'll see you tomorrow. Tfadal, Ahmed.
Yes, Doctor, regarding the causality, could there be a possibility of having a sub-non-causal system with a causal system inside a complete system? I mean, system contain two systems, one non-causal and the other is causal.
Okay, I understand what you're saying. Okay, Yeah, anyway, the lecture is over. So if you want to leave, you can feel free to leave. Okay. Basically, if I understood your question correctly, this is what you're saying. I have an input in here, x of t, and let's say I have in there as part of a system that looks like this. Let me in fact write it on the same block. Delta of t minus 3, for example. Okay. Delta of t plus 2. Can I have a system that looks like this? Okay. Where part of the system inside, this is basically what you're asking, right?
Yes.
Okay, yeah. I think I understand it. You see, you can theoretically have something like this, and you probably can analyze it, and everything will work fine. Why? Because what happens is that x of t in here gets delayed by 3 seconds. The other one kind of advances it by 2 seconds. So you have a signal that is delayed by 3 seconds and then advanced by 2 seconds. So the output here will be x of t minus 1, delayed by 1 second. صح?
Yes, but could we have the opposite?
Okay, this is basically the point that I'm trying to make. As long as inside your system you have parts that is maybe non-causal, but the overall system is causal, you're okay. I can analyze the system and I can even build it in the lab, let's say. I'm not going to build it like this, but what I will do is I will do something that is kind of a trick. I'll say, let me combine both of those together to come up with a single block that is causal. And I'll build this one that will have exactly the same effect. But clearly, you cannot have something that looks like this. To answer you, x of t, this is, let's say, delays by 3 seconds. So delta of t minus, let's say, delta of t minus 3. And then another block in here that will say delta of t plus 4. You can analyze this, but can you build it in the lab? No, you can never build this. In fact, you can never build non-causal systems that will predict for you. Okay, I mentioned you cannot build a system that can predict. You see, you can always build a system that predicts what the output will be before the input comes. Or you only see, for example, 2 seconds of the input, and that system will predict what the output will be after 1 second. But this is completely different from the system that we're talking about. When you do prediction, when you look, for example, at افرض مثلا سوق الاسهم الان and you're looking at سهم شركه سابق مثلا ويور looking at قيمه الان وقيمه بعد يوم وقيمه بعد يومين او خلينا نقول مثلا you looked at قيمه سهم سابق مثلا خلال الاسبوع الماضي and you say and it looks like tomorrow قيمه السهم راح ترتفع so let me buy that stock today so that I make profit tomorrow. You can think of this as a non-causal system because it's providing an output, okay, before the input happens. But do you guarantee that the output there is going to be what the stock tomorrow will be? Clearly not. You are just making a prediction. The systems that we're talking about here are not making prediction. They are telling you that the output will be equal to this much after 1 day or after 1 hour. Clearly, you cannot build a system like this. So this is not a system that is doing prediction. It is a system that is producing to you an output before the input actually comes. You cannot build those systems. You can only build systems that may have non-causal components inside as long as the overall system is causal. Did I answer your question, Ahmed? Or?
Yes, doctor. Thank you.
Okay. For sure. Any other questions, gentlemen?
For the next quiz, when will it be?
Okay, I'll probably mention it tomorrow. Okay, but most likely, and I remember that you mentioned that you don't want it on Sunday. You want it Monday, Tuesday. Probably it's okay, and I don't mind, honestly. If you want it on Sunday, I'll give it to you on Sunday. But tomorrow, inshallah, I'll discuss it. Tomorrow, I'll discuss it. Okay.
Thank you.
Sure, no problem. Yeah, but tomorrow I'll probably ask you to vote maybe whether you want it Sunday, Monday, or Tuesday, and I'm not always democratic, but at least in this something like this, it doesn't affect me, and I want to satisfy as many of you as possible. Yeah? Especially that most of you are probably taking the same courses. But if it's suitable for one of you, it's probably suitable for everybody else. But خلاص, inshallah, tomorrow we'll discuss it. Any other points or questions, gentlemen?
الله يعطيك العافيه دكتور، ما قصرت.
الله يعافيكم، حياكم الله، شكرا بدر.